Pulsars are unique celestial sources that produce distinctive periodic signals. Since their discovery, they've been considered as potential navigation aids and timing beacons to form a reference coordinate system and universal timescale. Further study of these astronomical objects has shown that their pulse timing can achieve sub-microsecond level performance, and interest and research into these sources has grown to conceive a fully autonomous navigation and timing system for deep space vehicles. Sources that radiate within the X-ray band of the electromagnetic spectrum have high potential for creating a practical spacecraft navigation solution, which includes accurate time and position determination on board a space vehicle using the precisely periodic sources, and precise attitude determination using both pulsating and steady sources. Microcosm, along with its partners Crosstrack Engineering, Catenni, and Astra Labs, are utilizing the characteristics of these pulsar sources for space navigation and timing. The baseline X-ray pulsar-based navigation, or XNav approach, uses observations of the X-ray emissions of millisecond period pulsars. With their wide geometric distribution in the sky and periodic radiation, pulsars appear to act as a kind of natural celestial beacon or celestial lighthouse. As a group, they conceivably act as a natural global positioning system, GPS, or Universal Positioning System, UPS, on a galactic and potentially intergalactic scale. Accurate time can be maintained on a spacecraft by coupling onboard high-quality clocks with a long-term stability of several well-characterized pulsars as an X-ray timing or XNav system. Celestial sources have proven to be significant aids for navigation throughout human history. Ancient mariners traveled vast distances across the globe with only the stars in the sky to guide them. A majority of these sources are fixed in their emissions and are considered optical point sources for navigation references. X-radiation observation requires much smaller detector sizes, order of a square meter, versus radio pulsars requiring tens of square meters of detector area. Along with pulsars, the X-ray sky contains several other types of variable objects that can be used for different aspects of spacecraft navigation. Types of pulsars include rotation-powered pulsars, typically fainter but more stable sources that radiate in radio and X-ray as they slowly spin down. Accretion-powered pulsars, neutron stars in binary systems, where stellar material is being transferred from a companion star onto the neutron star. These sources are usually brighter and shorter-lived, as well as often being highly variable in intensity over longer periods due to orbit eccentricity. Pulse timing is required to adequately characterize each source's unique characteristics, such as spin period, companion orbit elements, and a star's evolutionary stage. A timing model is constructed by fitting data obtained over the entire observational history of a particular source, accounting for every pulse of the source. These models predict when specific pulses from the sources will arrive within the solar system. The instrument for X-ray navigation and timing will consist of three primary components: a collimator or imaging system to select the pulsar to be observed, a detector and time-tagging system to measure the arrival times of the photons, and processing electronics and algorithms to turn the photon time histories into position and/or time measurements. The instrument system is designed to optimize the detectability of these sources and depends on the energy spectrum of the emitted X-rays. The navigation solutions proposed here are derived from X-radiation photon detection. An ensemble of many detected photons, formed either into images or average pulse profiles, can be used to compute directional, in the case of imaging, or timing, in the case of pulse profiles, information. Full three-dimensional 3D solutions are achievable from variable celestial sources, including vehicle attitude determination, position and velocity determination, and clock corrections for maintaining accurate time. It is this potential of the full suite of onboard navigation solutions from these periodic sources that is currently driving the interest and research into their capabilities. Attitude determination. X-ray emitting sources can be used as an attitude reference for resolving spacecraft orientation, as well as navigation and timing beacons. Thus, the XNav concept offers the potential for a single instrument to provide attitude, time, position, and velocity information to its host spacecraft. The operation and algorithms of an X-ray source-based attitude sensor is similar to that of a traditional optical star camera, A camera comprised of a pixel array of detectors combined with a coated aperture mask that images sets of X-ray sources to determine the camera's orientation by matching multiple source patterns in the field of view or identifying a unique source. Time determination. A unique capability that X-ray source detection can support to improve spacecraft mission operations is the ability to provide atomic clock quality time by monitoring these ultra-stable pulsars, a capability that's been demonstrated with several highly stable sources. Detection of these sources over long durations could reduce onboard clock errors, or at least stabilize any long-term clock drifts. This new system has several unique and potentially mission-enabling characteristics. Stability. XNav is based on observations of highly stable pulsars. While the accuracy of the pulsar observations are shot noise limited over short periods, seconds to hours, they are extremely stable over long periods, weeks to months. By slaving a local atomic clock to an ensemble of pulsars, a new clock with unprecedented stability over short to long timescales would be created. Autonomy. XNav would provide users with an independent and precise measure of time. This measurement is not dependent on an external system or on regular communication with other users. By tracking the same pulsars, multiple users can be guaranteed access to the same clock without communication between them. Universality. The pulsars used by XNav are celestial sources, making them available to any user anywhere in the solar system. Furthermore, any two users, no matter how widely separated or without line-of-sight communications, can use XNav to correlate events that occur on two or more spacecraft, enabling new missions for near-Earth observing spacecraft to spacecraft in the distant solar system. This also provides an opportunity to correlate measurements between platforms not originally designed for this task. In addition to providing a time reference and time transfer functions, the XNav system would also allow the capability of position and velocity determination, as well as relative navigation. Among the most promising applications for this X-ray navigation technique are science and exploration missions far from Earth. These types of missions can combine relatively small detectors, approximately 1,000 square centimeters in area, and relatively long observation times on the order of tens to hundreds of thousands of seconds, along with a benign disturbance environment, to achieve useful navigation estimates. Additionally, for missions that pass close to the Sun, spacecraft emergencies, and landing on or orbiting asteroids or comets, it is desirable and in certain cases essential to provide an autonomous capability for the position and velocity determination in real time on board. In such circumstances, for the execution of orbit correction maneuvers in a timely manner, the ability to estimate an onboard position, as well as maintain a very accurate clock, is essential and mission-enabling. Augmentation with existing systems such as DSN further enables missions to succeed or operate at lower cost. The XNav concepts could provide the technology for interstellar navigation for future vehicles that will venture beyond our own star. An example of these very far future missions could include that 100-year Starship concept, currently being investigated by DARPA and NASA, or solar sail missions being proposed by ESA. Operational benefits and challenges. There are numerous potential benefits from this technology. A navigation and/or timing system utilizing X-ray pulsars would be available anywhere cosmic X-ray sources can be observed, from low Earth orbits to interplanetary trajectories and planetary orbits. The system is passive, requiring only infrequent pulsar ephemeris updates, and can operate in an autonomous mode, independent of GNSS and NASA DSN systems. In addition, it can also be used in modes where it supplements or enhances DSN capabilities by stabilizing onboard time references for accurate range computations. The detectors are highly resistant to blinding or contaminating events. Detectors used within the XNav system are intrinsically radiation hardened due to their design for recording X-ray photon events. Even with the development challenges that this system faces, the conceived benefits of this new X-ray navigation and timing technology warrants its continued investigation.